Hi, this is another problem from the 2004 Purdue Programming Competition. It's the one-time pad problem, which is another classic computer science situation. It's a way to encrypt a message in such a way that if two different individuals know the encryption key, and they're the only people who know that key, then no one else can determine what the hidden message was with any certainty. There's a lot of little topics in here. The amount of code it takes to finish this one is very short. I think I finished it in 6 lines. But there's a lot of concepts, so it's a difficult problem to do if you don't know some of the individual concepts. So some of the concepts that this one gets into are the XOR operator, which we're going to talk about in a minute, as well as chars or chars, depending on who you talk to. I call them chars. But essentially a way to interpret letters as numeric values, kind of like when you hit on the keyboard, when you hit the H key. You don't actually send the letter H to the computer, you're sending a sequence of electrical signals that represent ones and zeros. So there's a lot of little concepts we're going to have to talk about. So the basic idea is going to be that our program needs to take in a message, attack at dawn, and a key, and somehow we're going to combine each of these letters with the letter in the key, so message to key, somehow do a combination that'll give you each of these numbers. And so 7 somehow represents A and F being combined together. 30 represents T and J being combined together. And so we're going to look at now how we can combine them together to get the output that we want. Okay, so here's some initial information you need to know. So a char or char is a data type in most languages, including Java, that allows you to represent individual letters or characters, so not like a string where it's a whole bunch of them, but one individual value. And then that's stored as a numeric value on the computer, as everything is, in a way that's easy to move between different characters. So for example, the letter A, lowercase a, is represented as the number 97. Obviously, that would be ones and zeros in an electrical format, but for us, it's the number 97 to look at. B is 98, so it's one more. C is 99, so it's all in a nice sequence. So the same thing happens for capital letters. All letters in the character format are in this nice numeric progression. You may be wondering what are some of the other numbers, like what about multiply and divide? The ASCII table, if you look that up, has a list of all the different values for each of the symbols. So ASCII, I believe, is a 8-bit, 7-bit, I'm forgetting off the top of my head, format. I think it's 8-bit with the extended format. So there's 256 different characters that it represents. Unicode is a format that allows you to have numeric values for Chinese characters or other symbols. But for what we're doing right now, chars and ASCII are going to be sufficient. All right, so first we know that individual letters can be represented by numbers. The next thing we're going to look at is the XOR operator. And this is an operator that does a very interesting mathematical operation on two numbers. So let's take the numbers 12 and 14. The XOR operator in Java is given by the I don't know what symbol this is called. It's shift 6. The caret symbol actually is what I think it's called, the caret symbol. You use it sometimes for exponentiation. It does not work in Java as exponentiation. It works as something called XOR. What it does is it takes the two numbers in binary. So 12 is an 8 and a 4, so that's 1100, and 14 is 1110. And when you XOR them together, what it does is it goes one digit at a time and sees if exactly one of them between the two numbers is a 1 and exactly one of them is a 0. So for example, for the first digit here, 1 and 1 are both 1s, so it does not meet our criterion. Only one of them can be a 1, but here two of them are. So that evaluates to a 0. The next digit, the same thing, because you have to have one of them be 1, not both of them. Here, you have a 1 and a 0. Well, only one of them's a 1, so therefore that's a good case. That'd be a 1. And then finally, both of these are zeros, so once again, does not meet our criterion for exactly one of them being a 1. So after doing the XOR operator, it will give you the value 0010, which happens to be the number 2. So exclusive OR means essentially you have one of them or the other, but not both. It's exclusive. And that's what's happening here. We had both, that's bad. We had both, that's bad. We have one of them, that's good. We don't have either of them, that's also bad. Now what becomes interesting is what if you take our original value 1100 and then XOR it with our new value 0010. Well, now when you do XOR 1 and 0, well, one of them is a 1, so that works. Oh, one of them's a 1, that works. Oh, one of them's a 1, that works. Neither of them are 1, so that doesn't work. Oh, look, we got the same number we had before, which was that 14? So the XOR operator is interesting because if you apply it twice, it undoes itself. So let me say that again. If you apply the operator twice with the exact same input, it'll give you the original value that you started with. So it's its own inverse, which is very useful for encryption. And here's why. Let's say you have a message that contains the letter S, and you have an encryption key of F. If you go through and do the XOR operator between S and F, so I did all the work here, lots of work, you get the number 21. This is a number you could send to somebody, and if they know that the encryption key used was F, then if they do 21 XOR F and do the whole operation, they'll get 83, which means the letter S back. So as long as both sides know the encryption key, you can hide a message, and nobody in the middle can figure it out. You can't intercept the message and determine what the answer was unless you know what the key is. So now we're going to go down here and implement the code. So we're going to have a message and a key we're going to read in from the user, and we're going to have to loop over every letter in the message. Now for this to work, they have to be the key has to be at least as long as the message. I don't remember if in the directions they said the key is exactly as long as the message. I think it is. The key has to be at least as long as the message, otherwise really bad things happen. So I am going to assume that they're always the same length. I don't know if that's safe or not. It doesn't say in the directions. I keep looking at them. All right. Well, we're going to assume they're the same length. If they're not the same length, then you might have to apply the key multiple times, which is dangerous because it allows a hacker to actually figure out what your cipher is, and they can steal your message. But assuming the key is as long as the message, I am now going to get the character in the message at position I. And we don't use this command ever, but the char@, command gives you the character at a given position in the string. So if your message was, and this is of course not what it is, but let's say it's hello world, then message.char@0 would give you the capital H. Message.char@1 would give you the lowercase e. And then if I do key.char@I, that's going to give me the corresponding character in the key. So what are we supposed to do with these? Well, we're supposed to XOR them. So that means you want to do m XOR k. And we just store that into a variable. Now, what we want is the numeric value, so we can assign it to a number. That's okay, because characters really are numbers, so you can assign a character into a number and it's no problem. In fact, I think when you do the XOR operator right away, it gives you an int. Yeah, because this gives you an error. So when you XOR the two characters together, it gives you a number. And if I remember the directions right, we just have to print this out. Yep. That's it. So we're going to go through and print this out. System.out.print the number. And I want there to be a space after this. So I'm going to check if I is less than message.length minus 1 to make sure I'm not at the end. Because if I'm at the end, I don't want to print a space. But here I do. And I think I spelled message wrong. And then to finish off my program, I'm going to add a print line command here. So that way it'll add a new line like the Purdue direction said. And that's it. I could have done this even shorter, but this is all you have to do for this program to do the one-time pad. So to do a very simple example, if I type in attack at dawn, and then FJDKSLKOSDMN and run it, you'll notice that I get this printout. It's a good thing I tested it because I wanted those all to be on the same line, and they're not because I put this print line in the loop. Oops. Yikes. All right, let's try that again. This time without the oops. Yay, and those are the same numbers that their output said, so I've done it correctly. So hopefully this helped you understand the one-time pad problem from the Purdue competition. Let me know if you have any questions.